In this lecture, I'll discuss something called known hashes. And I'd alluded to this previously in one of the earlier forensics lectures. And we already know what a one-way cryptographic hash is. And of course, cryptographic hashes are used to identify uniquely a file based upon its contents only, not on the metadata associated with it, just the contents of the file. So files with two different timestamps or with two different names can have the exact same hash if the contents are exactly the same. Well, the job of a forensics examination, the task thereof, is quite a difficult process and a time-consuming process if you're talking about looking at a standard set of, or a standard operating system installed, and then the additional files associated with it, because there could be tens of thousands or hundreds of thousands or even millions of files. And so rather than manually viewing the list of files, which could take years, what we can do is we can automate the process by using certain tools to identify one of two types of files: a list of known good files or a list of suspicious files. Let's talk about the first, the list of known good files. Take a standard installation of Windows 7. How many files are there? There's tens of thousands of files that are typically installed on a standard Windows 7 installation. When we first install them, we can assume that as long as we're using a CD that was created by Microsoft, or a good copy of that created by Microsoft, that there's nothing wrong with those files. We can create a hash of those files, and we can now put that to something called a list of known good files. What that allows us to do is to run automated tools that calculate the hashes on the files, compare them to that list of known good hashes to identify the files that we can pretty much disregard, because we know that those files are okay. They're not Trojan horses, they're not viruses, they're not worms, they're not hidden kitty porn, because they match the list of known hashes. The other type of hash is or hash list rather, is that of known suspicious files. So now we're talking about parts of Trojans, rootkits, viruses, worms, anything of a suspicious nature. And so that list of hashes is probably going to be shorter than the list of known good hashes. And so we can run the list of known suspicious file hashes, and we can compare that to the hashes of the files on our system to identify those files which may be suspicious. So you can look at this, the activity of identifying files one of two ways, either using the list of known suspicious files or those of the known good files. And the National Institutes of Standards and Technology has a website. Let me pull it up here quickly. The National Software Reference Library. And what the NIST has done is that it's created a list both of known good hashes and known bad hashes. And actually, I want to take that back, because what they ended up doing at one point in time, and this was several years ago, was actually combining the two on the same list, which I'm not sure why they did that. But as you can see here, the reference data set, the RDS, is a collection of digital signatures of known traceable software applications. So what NIST has done is to create these CDs of all the hashes. And if we go here, and by the way, this is free downloadable. If we go over to the downloads, and you can see you can download the ISO images of the RDS CDs. And just for kicks, if you'd like to download some of these, notice that they have reduced sets, that is minimal sets, and they have two of those. We have a minimal set that is 1.3 gigabytes. It's zipped. and we have a smaller that is 785 megabytes. But notice there's a disclaimer here. It lists the files that appear only once in the entire NSL collection. It cannot be used to determine all possible sources of a file. And so that's just a little background on the NSRL in the reference data sets. But what we're going to do today, I'm going to do a little demonstration of how you can create your own reference data set, so you can look at this from a security perspective. And as we discussed in some of the advanced security classes, there is software called host-based intrusion detection systems that will create a list of hashes right after you install your operating system, and it will store those with a cryptographic key. That is, it will be encrypted. And if you ever want to check to determine the validity of your operating system files, you can run this software Tripwire, which will essentially do the same thing we're doing now, only what we're doing here is manual. And Tripwire is all fine and dandy to run. However, you don't always have the luxury of doing this from a forensics perspective, because it does require you to install Tripwire. There are some CDs, forensic CDs, such as Backtrack, and there's several other CDs that will allow you to run an automated version of this recursive cryptographic checksum automated routine to identify any known bad files. So what we're going to do is we're going to do a simple version of it today, and I will show you how to do this. And the first thing we need to do is we need to collect, or rather we need to create our list of known hashes. So we're going to look at it from that perspective today. And it's quite easy to do it the other way around. And in fact, you might just do it both ways. Okay. So the first thing we need to do is we need to create the list of known hashes. So let's go ahead and let's create a directory. This isn't something you have to do, but I've already run through this exercise several times just to make sure that it works. So let's create a directory called example. Doesn't have anything in it. And now we need to create our list of known good files. And to do this as a simple illustration, we're going to look at the files from the var log directory. And so we're going to create secure hash algorithm 1 cryptographic hashes for each file in those directories. And so we need to run that as sudo because those files are owned by root. And so we can do a find log. That's where we're going to start. Some of this is magic. Do print 0. That means that each time you find a file in var log, output it to the screen, or rather output it in a format so that there's one file per line. It must be print 0, otherwise this isn't going to work. And then what this does is we're going to pipe this to xargs. Again, a little magic. And what xargs does is just simple command that's used on most Linux and Unix system that we can use to build and execute command lines from standard input. The -0 indicates that we should expect file names to be terminated by null instead of white space. And so we really need this -print0 and this -0 here for this command sequence to work. And then we can run SHA-1 on that. Now we want to output that to a file here. And so, whoops, yep, var log.SHA-1 and because this will try to run this against directories, we want to ignore the standard error, so we can do that. So we're going to find all files starting from var log. We're going to print each of those to a separate line, which is then piped to the xargs, which is essentially saying run this command SHA-1 on all these files. We're going to output that to a file, and we're going to Ignore standard error because there, as I said, there will be a few errors involved in this. We hit enter and it's done. It's very fast. Let's look at that file. And we see we have the SHA-1 sums for each of the files down here. And now what we're going to do is we're going to need to install a program called MD5 Deep, and that was written by a guy from the Air Force. And what that does is it does a number of things. What that does is it allows you to both compute in a recursive fashion or non-recursive fashion. The MD5 sums or the SHA-1 sums are actually, I believe, any length SHA, as well as use that output file that we saw there to check all the sums. So it's essentially acting like Tripwire would, but only in a very simple condition. So we're talking about incident response here. We need to identify a file quickly. This is one of the ways to do it. If you've got yourself a bootable Linux CD, you can run this all off of that. You can have your set of known hashes on a USB thumb drive, or you can then put that on the CD as well, and you can run this. And the way to install this, and I've already done this, is sudo aptitude md5 deep. And, whoops, install md5 deep. And what that will do is that will install 3 different files: md5 deep, SHA-1 deep, and I believe SHA-256 deep, but we're just going to use SHA-1 deep. If we'd like to look at the man page for SHA-1 deep, and it gives us all the information. Actually, it gives us 5 different applications. So we can compute 5 different SHA files, SHA hashes rather. And we can move on down here, and I'll show you a couple of options that we'll use today. One is it enables the recursive mode, because what we're going to do is traverse the subdirectories under var log. And we'll give it a couple of different other parameters that gives us like the yin and the yang of the output. One of which is it will compute the hash of everything that is in your computed hashes file, and compare that to the existing file, and if it's okay, it will print that. The other way to do this, so that would be the -m. Let me see where that is. So there's the -m or the -x. So it's -m, and this is and it really should be or. You can't use both of these. -m in the name of your hash file, or -x in the name of the file. -m displays the hash for each file that does match. The -x displays the hash for each file that does not match the list of known hashes. So let's get out of here. And so we need to run SHA-1 deep. We want to run that recursively. We want to run m, the files that do match. And so this is really just going to tell us whether these files match or not, whether they've changed or not. And we give it the name of the file. So that's called var log SHA-1. And then we need to give it the name of the directory. We hit enter. And it just gives us the names of all the matching hashes. Now, this is a little cumbersome, isn't it? Because if we're doing this to an entire system, I don't even know all the files that are underneath here. So what we're really interested in this case, are the files that do not match. So somebody could have placed a file there, or one of these files could have changed, and we're going to expect some of these files here to have changed. And why do we expect some of these files to change? Well, these are log files. So So you expect a lot of activity in here, so actually this probably wasn't that great of an example to use. We should have used it on a directory such as the SBin directory or something of that nature. I just wanted to make sure that there were several directories in here we could traverse to show you that this can be used recursively. And so let's clear this. And now what we can do is we ran that with the M argument before, which shows the matches. Now let's see if there's anything in here that doesn't match, so we can use the X and see if anything changed. So what this shows is from the time that we first ran it to the second time we ran this is that these files actually changed. That is, the contents of the files changed. And these are the new hashes. Okay, so let's run this one more time on another directory. Let's go to the SBin directory, and or let's go to the user SBin directory. I don't believe there's any directories in here. Okay, but you saw the capability of doing this recursively. Okay, so what we'll do is we'll go ahead and rerun this on the SBin directory. So we can scroll back up. And go to the find command, and we'll do this from the SBin directory. The SBin directory, the contents of that should not be changing that often unless you do an update. SBin SHA-1. Okay, and we'll run that. Let's take a look at SBin SHA-1 files. So this shows you the SHA-1 sums for everything in this directory. Okay, so now what we'll do is let's go in and just add a few files in there. And first of all, let's make a new directory in there. So sudo make directory SBin. Let's just see if this works. New directory. And let's copy some of these files in here, the SHA-1 files. Sudo cp.sha1. So here we go. So we've added a couple of files. Okay, so let's go back to example. We've got our SBin SHA file. All right, so let's go in and we'll run sudo sha1 deep. And we'll do the recursive and the M, which is those that do match. We'll give it to SHA-1, the SBin SHA-1 file, then the SBin directory. We see everything that matches. But we know we added two files in there, and you know what? They're not showing up, but that's not the way the -m works. So we can go back, and we can use the capital X or small x. And we see that it traversed all the directories, and it shows us that there are two new files, and these are the hashes of the files. Okay, just to run this one more time, what we will do is now we'll go back and we'll rerun the find command. We'll run that, and now it will pick up everything in the new directory, new dir here, so now we'll have hashes for these, and then we'll change one of those. Let's take a look at that file. And it should just be at the bottom. Whoops. SHA-1. and those are the SHA-1 sums for these new files. Now let's change one of those. Sudo echo Okay, so we're changing the contents of that file. You're just adding hello world onto the end. Oh, and it's not letting me do that. Okay, let me Okay, so we just deleted one of the lines. And now we can go back and run SHA-1 deep. And notice that it showed us that file has changed. Notice that the change in the SHA-1 sum, that's changed. What if we just deleted that file? Now the file no longer exists. So we've covered every possibility. We've added a file, we've changed a file, and we've removed a file. Let's see if it knows that that file has been removed. And interestingly, it doesn't. So it appears it works for adding files and changing files, but not removing files. And that's probably by design. So let's go back into SHA-1 deep. I've never used it to do that, but this is a live demonstration. Remove, delete. Okay, maybe it doesn't talk about deleted files. I'll let you do that as an exercise. As we probably saw in a previous demonstration, if not this class, a previous class, is you can still use MD5 sum with the -C option to check, to do similar to what we're doing with the -M command. And what that does is that it checks the existing files against those in the hash database to determine whether they've changed or not. The difference is that if you've got something that's been added to the directory, it won't alert on that. And I've tried that out, and maybe that's something that you'd like to do and to prove to yourself that that works. But that's one of the beauties of MD5 deep and SHA-1 deep, is that it will catch those files that have been added. So again, why do we want to do something like this from an incident response perspective? Well, we want to check the validity of the files. If there's certain files that have been added that weren't supposed to be added, if the files have been changed that weren't supposed to be changed, from an incident response perspective, we need the capability of being able to identify those files.